So here I put together a flowchart for all of the main trigonometric identities for us to go over in this course. Okay. These are all the formulas which are most commonly used in using trigonometry. Okay, and there's a lot of them here. I designed it as a flowchart to show in the direction of the arrows the progression that we have. We started with the fundamental trigonometric identities, with the defining the trigonometric functions and their reciprocals, then the Pythagorean, then the even and odd. Okay, and then we actually used the information about the definitions of the trig functions and the underlying geometry. Specifically, that was with the unit circle, in order to prove the first of these addition and subtraction formulas. The first of these we proved was this cosine of a sum formula by using the distance formula on the unit circle. Okay, and then we started proving other addition and subtraction formulas from that. Then we can use these addition and subtraction formulas to prove these cofunction identities, which all the cofunction identities also we were able to prove by using the graphs and considering horizontal shifts of the trigonometric functions and their cofunctions. Okay. The progression now continues that we can use the addition and subtraction formulas to define the double angle formulas, which are very important and show up in a lot of places, so they're important to know. We can also use them to derive these so-called product to sum formulas. Now, the product to sum formulas are not formulas that I'm going to be testing you on whether you have them memorized, for example, but these certainly provide good examples for us to be able to prove identities. So we'll go over one of those here in this video. Just pick one of these out of the list and say prove that it is true as an identity, because that's also an objective here for this course, is to be able to prove identities. But something like the double angle formula for sine, the sine of 2x equals 2 sine x cosine x, that would be a formula that we should categorize as we have to know. So you should memorize that one, for example. You'll be using it frequently enough in this course and in future courses if you continue to use trigonometry. Now, from the double angle formulas, we are then able to prove the so-called formulas for lowering powers, or power reduction formulas, that takes a higher power of a trigonometric function. For example, we have here, we can take the square of a sine function and rewrite it as an expression that includes a cosine to the first power. So we've reduced the exponent. That's what we mean by lowering powers, or power reduction. We can reduce from a higher exponent of a trigonometric function down to a lower exponent of a trigonometric function. And these, again, can be useful for us, in this course, for us to be able to prove that these exist, that we're capable of doing this. And where you might first start to see using these in an application would be in a second semester calculus course. For example, when dealing with anti-differentiation or integration strategy. Okay, for right now, these are not going to be primary identities necessarily for us to have to know, but we are going to be able to see where they are derived by using the double angle formulas, in fact. Okay, and the half angle formulas, those are also derived from the double angle formulas. Now, our objectives for today are based around us knowing these double angle. Okay, making sure that we know these double angle formulas, that we prove them, and that we can use them as well. There we go. We want to know those, and we want to know these half angle formulas down here. Now, these formula sets are closely related. Doubling an angle is the opposite of taking the half of an angle. All right, so if you started out with an angle, let's say you started with the angle 10 degrees. If you double that angle, you would get 20 degrees. Then if you reverse that by saying, well, if you started with 20 degrees, half of that would get you back to the original 10 degrees. So these two formulas are directly related, or sets of formulas are directly related to each other, really. And I'm going to be focusing on specifically the sine and the cosine formulas within each of these sets. The tangent formulas can always be derived by rewriting tangent as sine over cosine. Like the tangent of 2x, you can write that as the sine of 2x over the cosine of 2x, and that in fact starts the proof for this formula right here. So I would not say that we would have to memorize the tangent of 2x formula. Instead, use the fact that we already know that tangent is sine over cosine. Then if we know the sine of 2x and the cosine of 2x formulas, we can use those in order to figure out what the tangent of 2x is for any angle. Okay, so there's a lot of formulas here, and I'm sort of subdividing them into kind of three categories for prioritization. What do we really, what is most important for us to have to know in terms of what do we have to memorize? Okay, let's start with that. Okay, so maybe in green, okay, this will be the primary formulas. Let's say these are the formulas that we should memorize. And so you can either just, try to memorize them straight up, or by using them again and again, and specifically in any exercise where you need to use a formula, it is helpful to write it down first. The more times you do that, the easier it is to recall the formulas in general. Okay, so there's going to be a set of primary formulas here. Okay, and then that we want to memorize, and then there are a set of secondary formulas that we would want to know as well that we may not have to specifically memorize, but I would categorize as being able to derive quickly when needed. Okay, so you want to be able to derive these quickly, okay, as needed. Okay. And then, let's see, third, I would have a set of the tertiary set. Don't get to use that word too often. Okay, so the primary, secondary, tertiary set. Okay, they would include the formulas that you don't need to memorize and you don't need to be able to derive quickly, but just be able to prove. For example, if you're given the identity, can you prove that it is true, okay, by using other known identities and algebraic technique, as we studied in this course. Okay, so what would include the primary identities for this course? Okay. I would include the set of reciprocal identities in that. You should absolutely know these identities right here. All right, these are the ratio identities down here, which can also in some texts can be called reciprocal identities as well. The Pythagorean identities. Well, we want to know all of the Pythagorean identities, but primarily memorize this one here. Sine squared x plus cosine squared x is equal to 1. Okay. All right. Now, the other two Pythagorean identities are extremely important to know as well, but I would say we don't have to have them necessarily memorized. We can put them in the secondary group. We can derive these identities anytime that we need them. We can quickly derive them. How? We've covered that before. If you know the primary one, the sine squared x plus cosine squared x equal to 1, recall, you can then divide all the terms of that identity by, for instance, cosine squared x. If you divided all three terms by cosine squared x and use the reciprocal and ratio identities that we also know, like sine x over cosine x would be tangent x, for example, and 1 over cosine x would be secant x, you would really quickly be able to rederive this identity right here. Now, you can certainly choose to memorize all of these identities if that's what you would rather do. I'm just trying to suggest that, in terms of how much we actually have to store in our memory, right, I would say at least the ones that I'm outlining in green, and then the ones in orange, you should at least know the process for which you can derive those in any case where you might need one to use. And you're going to need to use these secondary ones in more places than being given them. You're not going to be given the identity and asked to prove it in this case. You're just going to have to know to recognize it, for example. Okay. And I've given you some strategies how you can do that in previous lectures. Anytime you have anytime you have an identity which might require that you know something like this, the tangent squared x plus 1 equals secant squared x, in order to prove an identity, let's say, you could always choose to turn everything into sines and cosines and then apply algebra and ultimately use the first Pythagorean identity. This is a case-by-case type of a thing. You can take a look at examples that I've already done in notes and in lecture as well. for where these identities might show up and how I might deal with those cases. All right, the even and odd identities. I would categorize all three of these even and odd identities as need to know. We should know. And one quick way to know whether they're even or odd is if we understand and recall even and odd symmetry, and we think of the graphs. Think of the graph of the sine of x, and how the graph of the sine of x, if we were to rotate it by 180 degrees about the origin, it would overlap itself. That means it's odd. The cosine of x graph, we think of that graph, if we reflect its graph over the y-axis, that's left to right if we flip it, it overlaps itself. That means it is an even function. And the tangent, like the sine, the tangent graph, if we were to rotate it through 180 degrees, it would overlap itself as well. The other way to show that tangent is odd is by saying, well, tangent is sine over cosine. And if sine is odd and cosine is even, then you're going to get that, therefore, the tangent is odd. A quick rederivation of that proof. Tangent of negative x is equal to the sine of negative x over the cosine of negative x, and we already have established that sine is odd, therefore the sine of negative x is negative sine x. That's the meaning of odd right there. That's odd symmetry. And the cosine is even. We have already established that. That's in our need to know and memorized bank of formulas that we have. So the cosine of negative x is cosine of x. Well, that means we have negative sine x over cosine x, but that would just be negative tangent x. Therefore, the tangent of negative x is equal to negative tangent of x, and that proves, therefore, that tangent is, in fact, an odd function. So you can either memorize that this is odd, or you could say you could rederive it real quickly, by either understanding a quick graph of the tangent function, if you will, or using an already known identity. So I would put that under both categories. You could memorize it, and you could rederive it really quickly as well. So the cofunction identities, those can all be rederived as needed. You can either use, you can use a right triangle trigonometry. We're essentially looking at the arguments here, u and pi over 2 minus u. Those are complements of each other. And the functions we're relating, such as sine and cosine, or tangent and cotangent, or secant and cosecant, those are all pairs of cofunctions. So you can use right triangle trigonometry to prove that these are true, but you can also use the upcoming formulas for sine and cosine to prove those are true as well, at any time that they're needed. The primary formulas from the addition and subtraction formulas that I would say you would need to know and have memorized at least, let's take a closer look at those, would include the sine of a sum and the cosine of a sum. So my suggestion is that you memorize these two formulas here, at least these two, and then recall that I've already shown how you can derive the subtraction formulas from those if needed. So if you don't memorize the sign of a difference, just know that you can always rederive it. The way to rederive the sign of a difference, for example, is to say, well, a difference s minus t is the same as saying s plus negative t. In other words, you can rewrite a subtraction problem as an addition problem with a negative in the second term. And then you can just go plug negative t into the first formula. So everywhere you see a t up here, you would replace it with a negative t. So you'd have cosine of negative t here and sine of negative t here. Then you use the previously known even and odd identities that I said were so important to know. Cosine of negative t is the same as cosine of t. And sine of negative t is negative sine of t. So you can quickly rederive the difference formulas, if you didn't have that memorized already. So that's a technique that I suggest. And the same process can be used for the cosine of a difference as well. So that's secondary. And then the tangent ones, those can also fall in the secondary group. And recall that anytime that you want to know something about a tangent, you can always go back to the reciprocal identity that tangent is equal to sine over cosine. So anytime that you have a tangent of anything, it's always equal to the sine of that argument divided by the cosine of that argument. So the tangent of s plus t is equal to the sine of s plus t divided by the cosine of s plus t. And that would always give you the same output. You can prove this formula is true, in fact, by starting with expressing tangent as sine over cosine, okay, and then applying algebraic technique and trigonometric identities in order to prove that the left-hand side equals the right-hand side. Okay, so the ones in green, the two in green, are the ones that I say you should absolutely memorize, and the ones in orange, you should be able to derive them as needed. Okay, now moving on to double angle formulas. For the double angle formulas, I say you should absolutely know the sine of 2x. It shows up so commonly in so many applications, you should certainly know that one. And you also should know all three of the double angle formulas for cosine. Okay, we'll show, I give you in the typed notes, I give you proofs for the cosine of 2x formulas. And the way that we prove the initial one, the cosine of 2x, is the same as the sine of 2x. They come directly from the sum formulas. For instance, 2x, 2 times x, okay, is another way of saying x plus x. So we could use the sign of a sum where both of the terms in the sum are equal to x, like sine of x plus x. That's another way of saying sine of 2x. Well, the sine of x plus x would equal sine of x cosine x plus cosine x sine x. Okay, and that's it. Then these two would end up being like terms because it would be sine x cosine x sine x, and those are the same as each other. So you get 2 sine x cosine x, and that's the entire proof right there done for the formula for sine. Okay, so this is what I mean in the flow chart, that these formulas here are really derived from the addition and subtraction formulas. Just consider 2x is the sum x plus x, and you can derive the first of the cosine 2x formulas. I did that in the lecture notes. Okay. Here we go. All right, prove the 3 double angle formulas for cosine. Okay, that's using the cosine of 2x formulas here. So I start with the first one. Cosine 2x equals cosine squared x minus sine squared x. How is the proof done? Well, 2x is x plus x. So you rewrite cosine of 2x as cosine x plus x. That means we're rewriting the argument as the sum of two terms, which gives us access to the already known addition formula. So we plug in x and x as s and t. So we get cosine x minus sine x. Right from the addition formula for the cosine. One of the ones I said was a primary formula that we should absolutely make sure we know. So memorize this formula here. And then, of course, cosine times cosine is cosine squared, and sine times sine is sine squared. So we've proven the first of the 3 cosine identities, double angle identities. Okay. Now, how do you prove the next one? The 1 minus 2 sine squared x? Well, it comes down to a Pythagorean identity. Another one I said was primarily important that you know. Cosine squared x can be replaced by 1 minus sine squared x. Why? Because of the Pythagorean identity, that cosine squared plus sine squared equals 1. If cosine squared x plus sine squared x equals 1, right? Go back to that one. Right. Where are we? Okay. Right, of course, if sine squared x plus cosine squared x is equal to 1, for example, okay, then we can also rewrite that Pythagorean identity. In one way, we could rewrite it as sine squared x, therefore, is 1 minus cosine squared x. Or cosine squared x is equal to 1 minus sine squared x. So both of those are, state exactly the same Pythagorean identity that we already knew, for example. Okay, going back to the notes. So I say, okay, we already have, now that we've proven that cosine 2x is equal to this, cosine squared x minus sine squared x, we now have that available to us, okay, to use in the future. We've already proven it's true. So starting with that, we then use the Pythagorean identity to replace cosine squared with 1 minus sine squared. Right? Cosine squared x is equal to 1 minus sine squared x. Then just combine like terms, and there you go. You have the second cosine double angle formula is now proven. The third double angle formula is proven in exactly the same way. You just replace sine squared x with 1 minus cosine squared x. And then the proof for tangent of 2x, again, is done by taking sine of 2x over cosine 2x. And then simplifying, you get this right here. All right. Okay, so the formula for the double angle of a tangent, I would put that into the secondary group. You can memorize it if you'd like, but you don't have to. Instead, you can always find the tangent of 2x by taking the sine of 2x and dividing by the cosine of 2x. That would always be sufficient. Okay. All right. Now, if I want to finish up with what are the primary group the primary group of identities here for us to need to know, there's only two more for me to include. Two of these half-angle formulas. You should absolutely want to know the half-angle formula for sine and the half-angle formula for cosine. And included with that, by the way, pay careful attention to this note right here. The choice of plus or minus depends on the quadrant in which the half-angle lies. It's important where this angle is in quadrant. And many times in these half-angle formula problems, in many cases, you'll be given the value of the original angle u. And even though we might be told the quadrant for which u is in fact, it's the quadrant for the half-angle that really determines whether this is plus or minus. Okay? So let's say that u is contained within quadrant 3, for example. All right? And then we know that in quadrant 3, the sine would be negative and the cosine would be negative. We also know that, like, for instance, the tangent would be positive. All right? All that would be true in quadrant 3. Okay? But what does that mean about u over 2? Because ultimately, if we want to know what is the sine of u over 2, that's what's the sine of half of u, we need to know what quadrant u over 2 is in to determine whether that sine is going to be positive, negative, or whatever. Right? So how do we do that? Okay. Well, if u is in quadrant 3, we can bound it either in degrees or radians. We can bound it between the smallest value of u possible and the largest value of u possible. So u must be larger than 180 degrees to be in quadrant 3, but has to be less than 270 degrees. Right? That would say that it is certainly within quadrant 3. All right. Or in radians, right? That would mean it would be pi and 3 pi over 2, for example. Now, using that, how do we find out where half of u would be bounded? Okay? Well, we can solve this inequality. To take half of u, we can take half of the 180 degrees. Okay? And we can take half of the 270 degrees. Okay? And that establishes that u over 2, the half angle, would be between 90 degrees and 135 degrees then. So what quadrant does that mean that u over 2 would be in? 90 degrees to 135 degrees, that would be somewhere between like here and here, between the y-axis and this line right here, represented by the equation like y equals negative x. So this is where we would be. And if u over 2 is in that region right there, then u over 2 is in quadrant 2. All right? It is clearly in quadrant 2. And that means that the sine of u over 2 would then be positive because it's quadrant 2. And the cosine of u over 2 would be negative. And the tangent of u over 2, that would also be negative. Again, tangent is sine over cosine, and we already know if sine is positive and cosine is negative, the ratio of the two is going to be negative anyway. So we could have established that by relating to the sine and cosine. So the point here is that if you're using the formula like sine of u over 2, if you're told that u is in quadrant 3, notice if u is in quadrant 3, the sine of u is negative, but we want to know the sine of u over 2. And the sine of u over 2, which is quadrant 2, would actually be a positive. All right. So if we are choosing u to be in quadrant 3, then in this formula we would choose positive, because u over 2 would be in quadrant 2 where sine is positive. Again, though, if we were choosing u is in quadrant 3 where the cosine of u is negative, notice that u over 2 being in quadrant 2, cosine is negative in quadrant 2 as well. So if u is in quadrant 3, meaning u over 2 is quadrant 2, then this formula for the cosine, we would require choosing the negative. Okay? So it matters that we're told what quadrant the original angle is in, and we have to then figure out what does that mean that the half angle, where does the half angle exist, in what quadrant? Because ultimately the quadrant of the half angle is going to determine whether we should choose plus or minus from these formulas. Okay, now half angle formula and double angle formula, they are directly related to each other. Again, that, a half angle is just a double angle, okay, in reverse, we could say. So really we can use these formulas here for the cosine of 2x, specifically the second and third, okay, is how the proofs are done. The cosine of 2x equals 1 minus 2 sine squared x, for instance. Notice that that formula there tells us that on one side of that equation, we have an angle called x, and on the other side, we have double that x. Now notice that if we let u equal to 2x, then this becomes cosine of u equals 1 minus 2 sine squared of, but then what would x be? If u is equal to 2x, then that means that u divided by 2 is equal to x, right? By that substitution, we can rewrite this identity as cosine of u equals 1 minus 2 sine squared of u over 2. All right? By making that choice to just change the variable like that. Then if we solved that for the sine of u over 2, which is done by subtracting 1, and then dividing by negative 2, and then taking the square root of both sides with a plus or minus, we would exactly get this formula right here. So really, this identity right here is the same as this identity is right here. They are the same equation as each other. Okay, in this case, we're looking at it in terms of doubling an angle that is given, but in this case, we're looking at it in the reverse direction, which is to take the half of an angle. Okay. The proof for the cosine of a half angle formula is similarly done by using the cosine of 2x equals 2 cosine squared x minus 1, for example. In exactly the same way with the same substitution. Okay, so I go through examples like that in your notes. Okay, for the half angles. After doing some examples for double angles. Okay, prove the half angle formula for the sine. Okay, and I do exactly what I just suggested, which is we make a substitution. We say, well, look, doubling an angle is the same as taking the half of an angle, but in reverse. So we're just going to change the equation to represent that we're actually considering the half of an angle rather than the double of an angle. And then we solve it for the half angle. And in the process of doing this, by the way, we actually end up encountering another one of these formulas in the flowchart. This is the power reduction or the lowering powers formula for sine. Okay, recall that, right? If we, this proof is done here by making u equal to 2x. In other words, u over 2 is equal to just x. So if we rewrite this line right here in terms of the variable x that we had started with, we have this equation right here, and that's exactly the power reduction formula for the sine. So it's within the proof for the half angle for sine, we end up getting the power reduction formula for sine. Similarly, within the proof for the half angle formula for cosine, which is done in exactly the same way this is done, just using the other double angle for cosine, using the 2 cosine squared x minus 1 instead, in the midst of the proof for the cosine of a half angle formula, we would end up encountering the power reduction formula for the cosine as well. So those formulas, the formulas for lowering powers, are formulas that you don't necessarily need to know for this course. And they're helpful to know. They certainly are helpful to know, and that you will need to use them in future courses. But for right now, I would put those in the category of, so in the tertiary category. for the formulas for lowering powers. That is that you should expect you might have to prove one of these, and the proofs for these are done by manipulating known identities for the double angle for cosine, for example. Okay? Other than that, if you're given the formula, if you're just given the formula, you might, maybe use it in order to lower a power, for example. But, I think we'll just stick with be able to prove these formulas for lowering powers at this point. The tangent of u over 2, that should be something you would be able to derive if you needed it. And in any case where we might say need one of these formulas, the tangent of u over 2, for example, I would say, well, look, if I already know the sine of u over 2 and the cosine of u over 2, why don't I just use the ratio of those two instead? Okay, so that's if we had already done the work of finding the half angle for sine and the half angle for cosine, for a given angle. Okay, then I would just find the tangent by taking the ratio of those two. Okay, but you can either rederive these formulas here, or let's just say just be able to prove these formulas. Okay, my orange and my red are kind of similar. I should use a lighter colored orange. Okay, so let's put this in the tertiary category right here. Okay, you don't need to memorize these. You don't even really need to derive them that quickly. What you can derive, if you need the tangent of a half angle, is you can just take the sine of a half angle divided by the cosine of a half angle, and that would be sufficient. It'll work every time anyway. These are identities. And then the formulas for product to sum, that is, when you have a product of trigonometric functions, how can you re-express that as a sum of trigonometric functions? Okay, those are all going to be in the tertiary category. Okay, these are all to just be proved. So I hope you can tell the difference between my red and my orange here. Okay, maybe I'll go a little lighter on this orange. Okay, all right. Hopefully you can tell the difference between what I'm saying is, okay, some that show up frequently enough that you might want to rederive them, and others that you just need to be able to prove that they are true. But in future courses that may change depending on what your course of study is. All right. So we are focused on these formulas for the double angle for sine and these formulas for the half angles for sine and cosine. Sine and cosine, sine and cosine. Okay. All right. The double angle and half angle formulas, what are they meant to do? Okay, well, if we are given some angle, let's use x, let's call it theta, let's call it t if we want it to be an arc length, okay? So whatever the original angle is, maybe that is given. We'll call it x right here for the moment. Let's just choose a number, like 30 degrees, right? Let's say that we're given x is equal to 30 degrees. Well, then what is the cosine of that x? That's what is the cosine of 30 degrees, right? We've already done that before. We know that 30 degrees is a quadrant 1 angle. We know the x-coordinate is larger than the y-coordinate when we're at this point, for example, okay? So the x-coordinate here, or the cosine of 30 degrees, is positive root 3 over 2. What is the sine of 30 degrees? Okay. That would be the y-coordinate there. That's equal to 1/2 or 0.5. Now, what would 2x equal? Okay, we are given x. What is 2x going to be? Well, that's double 30 degrees. So what's 2 times 30 degrees? That would be 60 degrees. Then what is the cosine of 2x? That is, what is the cosine of 60 degrees? Well, the cosine is 60 degrees, okay? Where would 60 degrees be? It would also be in quadrant 1, okay? But it would be, right, more like there, more or less, right? So here the x-coordinate is a little less than the y-coordinate, if we consider the symmetry here, okay? Because we have a larger angle here than we have here. The cosine of 60 degrees then is equal to the 1/2 or the 0.5, and the sine of 60 degrees is equal to root 3 over 2. Okay, so what we're trying to do with like double angle formulas, and then we'll also try to do with the half angle formulas, is we're trying to relate, for instance, maybe the cosine of x, the square root of 3 over 2 number, okay, relate that to the cosine of 2x. All right, how does this relate to this? Or how does this relate to this? And similarly, how does the cosine of 2x relate to the sine of 2x, and how does the sine of x relate to the sine of 2x? That is, can we find, algorithmically, some way to figure out, if I already know, okay, if I already know the cosine of an angle, for example, is root 3 over 2, does that help me to figure out what cosine of double that angle is going to be? Is there a relationship here? Right? If we double the size of the angle, for example, here's a question, if we double the angle, does that mean that we double the output? Right? So is it true? In other words, I'm saying, would it be true that the cosine of 2x is equal to 2 times the cosine of x? Is that a true statement? Okay. Well, the cosine of x, right here we have an example where the cosine of x is root 3 over 2. But if we double root 3 over 2, we would get the square root of 3. And the square root of 3 is not equal to 1/2, so this is certainly not true. Right? This would be an example of something that is not an identity. All right, this is a false statement in general. So there may be values of x that would make this true, but there's many values of x that do not make this true. In other words, this is a statement that we could prove is false by the use of a counterexample. And one counterexample could be if x is equal to 30 degrees. If x is equal to 30 degrees, the two sides are not equal to each other. Okay? So doubling an angle doesn't mean you double the output, or you don't double the output of the function, that is. Okay? So what is the relationship then? Okay? And how can we use that relationship to describe what happens for other angles of x, right? For instance, what if x is equal to the 60 degrees? Okay, so what if we started with an angle that was 60 degrees, that's found in quadrant 1, okay? Then doubling that angle, we would be looking at 120 degrees, and 120 degrees, well, that would push us into quadrant 2, for example. And so now the signs, S-I-G-N-S signs of the trigonometric functions are not going to all be the same as they were back here at the original angle, right? There's going to be a change in the signs. Okay? Now the cosine of 60 degrees, again, is equal to 1/2. And now the sine of 60 degrees, again, is equal to root 3 over 2. But now that we double the angle, okay, reevaluate, what's the cosine of 120 degrees going to be, for instance? Well, that puts us in quadrant 2. The reference is 60 degrees, so we have the same magnitude as 1/2, but cosine, okay, but the cosine in quadrant 2 is going to be negative. And the sine, by the way, in quadrant 2, that's going to be positive. So the cosine of 120 degrees turns out to be negative 1/2. Right? So again, we can say, is there a relationship between this number, what the cosine of 60 degrees was, and this number? When we doubled the angle, how do we predict what the new output is going to be? Notice that here, we changed from a positive to a negative, is all we did. But up here, when we did the same process of doubling the angle, we didn't just make this number negative. Right? We did something else. Somehow we changed this into that number. So we want to come up with, is there an algorithm, is there a formula that would tell us what the double of an angle is going to be under any circumstance, no matter which angle we were originally given. Okay? And that's the use we have for the double angle formulas. Now the sine of 60 degrees is root 3 over 2. What is the sine of 120 degrees going to be? Okay, that would be, by symmetry, is exactly the same as the sine of 60 degrees. Same reference angle, and sine is positive there. So this is going to be root 3 over 2. So if we were going to relate the sine of 60 degrees to the sine of 120 degrees, it would turn out, well, they end up being exactly the same value as each other. Okay. Now we can extend this beyond just the known angles that we have. What if we wanted to take an angle, how about 100 degrees? 100 degrees as x. That is, we want to know on one hand, what is the cosine of 100 degrees going to be? Right? Oh, and what quadrant is this in? Right, 100 degrees. That would be just barely in quadrant 2. Okay, a little more than 90 degrees, 10 degrees more than 90 degrees. Now, what is the cosine of 100 degrees? Well, right now I'm going to approximate that with the calculator, for example. I'm going to put my calculator in degree mode and say, what's the cosine of 100? And it's giving me approximately negative 0.1736. I'll go out to 4 decimal places, but in fact the number continues on beyond that. What is the sine of 100 degrees going to be approximately? So the calculator says that is approximately 0.98 0.48 to 4 decimal places of accuracy. It goes on beyond that. Doubling the angle 100 degrees, we would get 200 degrees. Where is 200 degrees found? That's more than 180, but less than 270. So this would be in quadrant 3. And in quadrant 3, all right, just like we know over here, okay, so the the cosine in quadrant 2 is negative. The sine in quadrant 2 is positive. In quadrant 3, both the cosine and the sine, okay, both of those are negative, right, in quadrant 3. Okay? All right, but what is the cosine of 200 degrees? Using the calculator, I'm getting negative 0.93969, so that's 9370 to 4 decimal places. Okay, using the calculator, okay, we want to ask again the question, is there a way that we could have related this number here, the cosine of 100 degrees, and the sine of 100 degrees as well, right? Could we relate that somehow to this answer right here, right? And it's not so obvious how we can connect these two numbers to each other. Okay, and the formulas give us an abstract way to be able to do this no matter what angle we are given originally. And let's see, finally, the sine of 200 degrees. The calculator says that is approximately negative 0.3420 to 4 decimal places of accuracy. And again, is there a way we can relate the cosine of 100 degrees and the sine of 100 degrees to what the sine of 200 degrees is? That's the question. And what about the reverse? What about the reverse of exactly those questions as well? Is it possible, all right, what color should I use here? All right, we'll go orange in reverse. Would it be possible to relate, when we already know what the trigonometric functions of double an angle are, would it be possible to relate that back to what the sine and the cosine, all right, of the original angle was? That is, what if we took half of an angle? What if we were given the 60 degrees? What if we were given the 60 degrees and we wanted to establish as a result of that what would have happened at 30 degrees, right? What's a formula that would tell us how to relate the cosine of 60 degrees and the sine of 60 degrees, for example, okay, back to finding out what the cosine of the 30 degrees was? That would be the process of taking a half angle. Okay. And again, I'm saying to do the half angle thing, we're saying, what if we were already given the larger angle, the doubled angle? What if we were already given an angle and we wanted to know what would we have had if we cut that angle in half? How do we get back? Okay, how do we get back to these values here in column 2 and column 3 in general? Right? How do we relate these, the cosine of 120 and the sine of 120, how do we relate those back to the sine of 60 and the cosine of 60? All right? And if we're given the cosine of 200 and the sine of 200, how do we relate those back, okay, to the sine of 100 and the cosine of 100? Okay, what happens if we cut an angle in half and want to reevaluate the trigonometric functions? We're going to have to consider the quadrant that we started in and establish from that, as already shown, what is the resulting quadrant of taking half the angle. That's required. And that's really going to be necessary because of the fact that the formulas themselves for the half angles, I have them here as well, right? Here we go. The formulas for the half angles, okay, require a plus or a minus, right? Whether it's the sine or the cosine, they both require a plus or a minus to be chosen. Okay, so we're always going to, in a half angle problem for sine and cosine, we're always going to need to determine the quadrant of the half angle, okay, in order to figure out whether the output is going to be positive or negative. Okay, and note we can always use fundamental trigonometric identities to find the other trig functions of 2x, and also the same is true for x over 2 or u over 2. Okay, Now, I want to go a little bit further than the notes already showed. I want to say, well, is it possible for us to go beyond just a double angle? What if we wanted to derive a triple angle? Again, I did the derivation of the double angle for cosine, did that on the lecture notes, and I asked you to do the sine derivation. I told you how to, but how to do the derivation of the formula for sine of 2x, do that on your own. Okay, and let me know if you have any questions at all. Okay. Now, how about if we wanted to extend this idea to a triple angle? Could we find a formula for the cosine of 3x? The answer is, well, yes, we could. What we can do is we can say, well, 3x, using the same strategy as we did for 2x, we can rewrite 3x as a sum. For instance, 2x plus x. And then the cosine of 2x plus x, we can then use the sum formula for a cosine, which is one that we're supposed to have memorized, right? It's helpful, when trying to memorize the formula, it's helpful to write it out, right? So you may want to write it out. What is the cosine of s plus t? That's the cosine of s times the cosine of t minus the sine of s times the sine of t. Write it out every time you need it. Okay, it'll make it a little easier to remember it. Okay, cosine of 2x plus x, therefore, is going to show up as what? Cosine of 2x times the cosine of x minus the sine of 2x times the sine of x. Okay, so that would be a formula that we have. The cosine of 3x is equal to this. Now, let's say we want to get this all in terms of, let's say, if we want to reduce this to where all the arguments just include x in it. We can go further than this then. The cosine of 2x, for instance, we have options of how we want to write that. One possibility is to write it as the cosine squared x minus sine squared x. That is a double angle identity. All right? One that I've already proven in the notes, in the lecture notes, okay, the typed notes. Okay? So you can see the proof for that, and this is one that you should have memorized, okay? Because it shows up so frequently. It's my suggestion, my recommendation. And then we have cosine squared x minus sine squared x times cosine x. You could have chosen, by the way, either of the other, any of the cosine of 2x formulas. Okay, any one of them would be fine here. Okay, I'm just choosing this one. The sine of 2x, that's another one you should know now. The sine of 2x is 2 sine x cosine x. Know that identity, okay? And then this is times the sine of x. Okay, I'm going to outline those in green, okay, for your notes here. But you know that this is one that you should know. This is one that you should know already. Okay, by virtue of working on this section of material. All right, now I'm going to go ahead and expand here and see if there's any simplification. Cosine x times cosine squared x gives us cosine cubed x, and then we get minus, let's see, sine squared x cosine x. Then we get minus 2 sine squared x cosine x. Oh, and these are like terms, and they can combine. That's nice. So we get the cosine cubed x minus 3 sine cubed x cosine x. Okay, so we have now derived a triple angle identity for cosine, just as an exercise. Okay, this isn't a new formula for you to memorize or anything. It's the process that I'm referring to. Okay, it's possible to do this for any multiple angle. You can find a formula for the cosine of 4x or the cosine of 5x if you want to, just to say that it is possible to get a formula that tells us how to figure out, okay, for example, okay, if x is equal to 30 degrees, okay, how can we use that, okay, or let's not even use 30 degrees because that's too easy of an angle maybe to work with. Right? Let's say if x is equal to 12 degrees, okay, then what is going to be the cosine of 36 degrees, for example? That is what happens when we triple the angle, okay? We can use the formula, okay? We can use the formula where x is equal to 12 degrees, for example, right? So you can triple an angle now and use this formula in order to figure out what the output is going to be. In an abstract sense, okay? So this is not just, I would just go to the calculator. I mean, you could do this no matter what number it was, even if you allowed it to continue to be a variable. And that's primarily more important here than just being able to use a calculator to do one example, right? We can do an unlimited supply of examples without a calculator because we have a formula. Okay. So it would be possible to prove, how about for the sine of 3x? Do the same strategy. Is the sine of 2x plus x, for example. So we could say, well, now we have the sine of a sum, right? And what's the sine of a sum? The sine of s plus t is the sine of s times the cosine of t plus the cosine of s times the sine of t. So sine of 2x plus x, right? We could write that as the sine of 2x times the cosine of x, okay, plus the cosine of 2x times the sine of x, for example. All right, we can then write sine of 2x is 2 sine x cosine x, and then that gets multiplied by the other cosine x that's already here. Plus, and then we have a cosine of 2x. Okay, how about if I take cosine squared x minus sine squared x, and then times sine x, for example. So I'm re-expressing the sine of 3x in terms of only functions of x. So this gives us 2 sine x cosine squared x, plus this is going to be a sine x cosine squared x as well, minus sine cubed x. Okay, we have like terms here, so this gives us 3 sine x cosine squared x minus sine cubed x. So we now have a formula for a triple angle identity, if we wish. Okay? All right, so this is just, all right, so some of the stuff that we can do, we can extend upon the base formulas that we already have so far, and we can build new formulas. Okay? Maybe we should do an example for product to sum formulas. And you have numerical examples in here as well in the notes. You can let me know if you have any issues with anything here, or of course anything in the homework as well. Okay. But I'm going to go ahead and prove one of these product to sum formulas now. Let's take I'll take this one right here, this third one, cosine u cosine v. Well, let's prove that. Prove that the cosine, it was cosine u cosine v is equal to 1/2 times the cosine of u plus v plus the cosine of u minus v. Okay? Now, to do this proof, I'm going to start with the more complicated looking side, which to me is the right-hand side. And the right-hand side is 1/2 cosine u plus v plus the cosine of u minus v. Okay, so we have 1/2 times. Now, what is the cosine of u plus v? That's the cosine of a sum. And the cosine of a sum is written as the product of cosines, so cosine u cosine v, minus the product of sines, sine u sine v. Okay, that is a formula that you should know already, right? That's from the addition formulas or the sum formulas. Okay, and then we have plus the cosine of u minus v, right? Well, that's the same as we've derived. That's the same as saying the cosine of u plus negative v. All right, okay, so we're going to get a cosine of u. Cosine negative v is the same as cosine v because cosine is an even function. And then we're going to have minus the sine of u, but then it's going to be sine of negative v. And because sine is odd, the sine of the sine of negative v is the same as negative sine of v. So this is going to give us a plus sine u sine v. Okay? Now let's see if we can combine any like terms here. Okay, all right, so we did. All right, this was a known formula here. Okay, we have a cosine u cosine v plus cosine u cosine v. So we combine those. We get 2 times the cosine of u cosine of v. Then we have what? We have minus sine u sine v plus sine u sine v, and those then are going to cancel each other out. 1/2 times 2 is equal to 1, so this just equals cosine u cosine v, and that is the left-hand side, so that proves the identity or the formula. Okay, so we're able to prove this starting on the right-hand side, working towards the left-hand side by using known identities and formulas that we've already studied recently. Okay. All right, so I'd like to take a look at maybe one example, a double angle and one half angle. Okay. How about if secant of x is equal to 3 and x is in quadrant 4, find the sine of 2x, cosine of 2x, tangent of 2x. Okay, exact values only. Okay, well, the sine of 2x, formula for that is 2 sine x cosine x. Okay, we know the secant of x is equal to 3 and the quadrant. Now recall, if we're given a trigonometric function and its output, and we know the quadrant, we can find all other trigonometric functions of that same argument, right? We can find what the sine of x is equal to, and the cosine of x is equal to, the tangent of x, etc., etc. Now we only need the sine of x and the cosine of x to complete part A, finding the sine of 2x. So what's the cosine of x? It's 1 over the secant of x, and that would mean the cosine of x is 1/3. So we have an element of this. We don't know what the sine of x is yet, we have to figure that out, but we know the cosine of x is equal to 1/3. Okay. Now the sine of x. Okay, we're in quadrant 4. Let's consider that. In quadrant 4, the sine is going to be negative, so we know the sine of x is a negative number. Okay, and what is that going to be? We can relate sine to cosine. Remember, by a Pythagorean identity. The sine of x is going to be negative the square root of 1 minus the square of the cosine of x. If you didn't want to do it by identity, you can do this by drawing yourself a right triangle. All right, you can use the geometry. If you have the angle x and you know the cosine of x is 1/3, then you know the adjacent side is 1, the hypotenuse is 3, and you can solve for the opposite side here. Again, as mentioned before, you're actually solving for using the reference angle for x here. Okay, you're still going to have to consider quadrants so that your value of sine is in fact made negative. So you can use the triangle here in the Pythagorean theorem to solve for what's the sine of the reference number, but you're still going to have to make sine negative because of the quadrant. Okay, so 1 minus 1/3 squared. Well, 1/3 squared is 1/9. 1 minus a ninth is 8/9. So the sine of x is going to be negative the square root of 8/9. And that simplifies as negative 2 root 2 over 3. So we get 2 root 2 over 3. So sine of 2x is 2 times negative 2 root 2 over 3 times 1 over 3. That gives us negative 4 root 2 over 9. Okay? So next, let's say we wanted to find the cosine of 2x. We have options here. We can use either the cosine squared x minus sine squared x, or we can use 2 cosine squared x minus 1, or we can use 1 minus 2 sine squared x, any which one that we want. It really doesn't matter which one you choose. We know what the sine of x and the cosine of x both are. Okay, cosine of x is a simpler fraction, and for that reason, I'm going to go for this one right here. Then, right? I'm going to take that. So the cosine of 2x is equal to 2 times cosine squared x minus 1, where the cosine of x is 1/3, so we got 1/3 squared minus 1. I find that to be the easiest way to do this particular exercise, given the information that we have already. Okay, and that equals then, let's see, 1/3 squared is 1/9, so this is 2/9 minus 1. Okay, 2/9 minus 9/9 would be negative 7/9. Okay, and that would be that. Okay, finding the tangent of 2x, we can simply say that we know that the tangent of 2x is the sine of 2x divided by the cosine of 2x. Okay? And so we take our quantity for, let's see, sine of 2x was negative 4 root 2 over 9. Negative 4 root 2 over 9, and divide that by the cosine of 2x, which is negative 7 over 9. Negative over negative will give us a positive. The 9's will cancel each other out, and we'll end up with 4 root 2 over 7. Okay? And that would be it. Okay? Notice that the signs, S-I-G-N-S signs of these quantities should correspond with the quadrant for 2x. Right? Let's see. In which quadrant is the angle 2x going to be? Were we told? No, we were told that x was in quadrant 4. X was in quadrant 4. What does that mean that 2x is in? Do not assume that you double the quadrant. In other words, that doesn't put it in quadrant 8. You don't double the number of the quadrant. Okay? It's the angle. Okay? It's the angle that matters okay, where it terminates, okay? But in fact, we can tell what quadrant 2x is in by looking at the signs, S-I-G-N-S, signs of sine and cosine. The sine of 2x is negative, right? The cosine of 2x is negative, okay? Therefore, 2x must be in quadrant 3, right? Only in quadrant 3 would you have the sine of the angle is negative and the cosine of the angle is also negative. Now, it's possible to have an angle in quadrant 4 that when you double it, you end up back in quadrant 4 again, for example. So it's not always going to double and end up in quadrant 3. We really are looking at the outputs of the double angle evaluations in order to determine the quadrant of the double angle here. And let's take a look at an example in reverse, a half angle 1. Okay? To find the cosine of t over 2 if the sine of t is negative root 15 over 4, okay, and where 3 pi over 2 is less than or equal to t is less than or equal to 2 pi. In other words, okay, for this statement right here, 3 pi over 2 would be negative y-axis direction, and 2 pi would be after a full rotation back to the positive x-axis. It means that we can expect that t is contained within quadrant 3. Okay, I don't even really need the equal to bars there, okay, because I can see from the output of this that it's not going to be on one of the axes. Okay, but we are certainly, there I quadrant 3. This is clearly quadrant 4, that is, quadrant 4, okay, is where t is located. Right? Now, we want to find the cosine of t over 2. Let's write out the formula for it, okay? Cosine of t over 2 is equal to plus or minus the square root of 1 plus the cosine of t over 2. So I've just replaced in the formula that is given in the notes. This was a u. We're replacing it now with t. Now, is this plus or minus? It's not because t is in quadrant 4. That's not what determines this. What determines it is the quadrant of t over 2. In what quadrant is t over 2? Well, we take the original inequality and divide everything by 2. So we have 3 pi over 2 divided by 2 on one side. We have 2 pi divided by 2 on the other side. Okay? And that establishes that t over 2 is, well, it's less than pi, but it's greater than 3 pi over 4. Okay, what quadrant is that? 3 pi over 4, okay, would be here, about 45-degree angle from the negative x-axis. That's 3 pi over 4. And pi is the negative x-axis. That means that t over 2 is over in this region right here. That means that t over 2 is found in quadrant 2. That's important. Therefore, the cosine of t over 2, okay, therefore the cosine of t over 2 must be negative. All right? Even though in the original, right, here, right, with the original value of t was in quadrant 4, right? Well, the cosine of t, when t is in quadrant 4, the cosine of t is positive, right? Because we went from quadrant 4 to quadrant 2, the sign of the cosine, okay, has switched to negative. So the cosine of t over 2 must be a negative number. So we have that. So therefore, the cosine of t over 2 is equal to negative the square root of 1 plus cosine of t over 2. Now we need to know what the cosine of t is. How do we know the cosine of t? We're given the sine of t and the quadrant for t. Right? We have to find out what the cosine of t is now in order to plug it into this formula. Well, the cosine of t is equal to plus or minus the square root of 1 minus the sine squared of t. Okay? And in quadrant 4, which is where t is in quadrant 4. Okay? Cosine is positive there, so we choose the positive of these, and the sine of t is already given to us. the sine of t was given as negative root 15 over 4. So negative root 15, right, over 4, and then that quantity gets squared. So the cosine of t is equal to positive the square root of 1 minus negative root 15 over 4 squared. And that's equal to the square root of 1 minus 15 over 16, right? We square a negative, gives us a positive, and then we had another negative out here for a subtraction. 1 minus 15 over 16 is 1 over 16. So this is the square root of 1 over 16, and that equals 1/4. And again, that is positive because t is in quadrant 4. 1/4, then, cosine of t is equal to 1/4. So we go back to our formula. The cosine of t over 2 is negative the square root of 1 plus 1/4 over 2. And then we can simplify that from here. Okay. So it's negative. Then 1 plus 1/4, by the way, is 5/4. So we get 5/4 over 2. Okay. Sorry for cramming that in there, kind of. Negative the square root of 5/4 over 2. And that's what? Negative. So 5/4 divided by 2 is 5/8. So negative the square root of 5/8. Okay. All right. And that simplifies as what? Negative root 5 over 2 root 2. We can rationalize the denominator. That gives us negative square root of 10 over 4. Multiply by root 2 over root 2 to get this rationalized denominator here. Okay. So therefore, cosine of t over 2 is equal to negative root 10 over 4. Okay. It's negative because t over 2 is contained in quadrant 2, where cosine would be negative. Okay. And that's the exact value for the cosine of t over 2. All right. All right, so that does it for double angle and half angle, with a couple examples there and some proofs done, along with your lecture notes as well. Okay. You can let me know if you have any questions as you're working on the homework, and also I hope you consider the strategy I discussed for how you know which of these formulas you specifically want to memorize, which are the ones you would want to be able to derive when needed because they show up commonly enough, and which ones are, can be delegated as just you just need to be able to prove them or solve problems with them when given those formulas. Okay, so the tutors are still available as well if you need assistance from them. Okay, take care.